Most people know hydrogen from the classic story of the Hindenburg, which was an old blimp that was filled with hydrogen and exploded, of course. That sort of gave everyone a fear of the dangerous potential of hydrogen, but it also has incredible potential to provide a source of energy and be a carrier of energy because it's so volatile.
I didn't know concrete was the most used substance on the planet until I started, doing this podcast. But it seems like the same feedstock we've been feeding concrete is the same feedstock since we invented modern day concrete in the 1700s. Like we haven't really thought like, what can we put into this? And so maybe, can you spend a little bit of time kind of sharing your thoughts on how Hydrova can potentially change how we think about, cement?
Yeah, absolutely. So cement is an interesting topic in terms of emissions and just, it being the most consumed substance by humans, the most widely used building material, and being so hard to decarbonize because the carbon emissions actually come from sort of burning these calcium carbonate rocks that releases emissions that's harder to electrify than other industries. First, let's define some terms. So cement versus concrete. So most people sort of toss them around interchangeably.
Yeah, sorry, I did that, but I know they're two different things.
No, definitely, yeah. Which you must have learned doing the other.
Yeah, again, I didn't know that before.
Yeah, so cement, and I'm sure you'll explain this in the next episode too. But cement is the glue that holds aggregates like gravel and sand together to form concrete, which is the final finished product. Cement is made of also various ingredients, one of which being clinker, which is where the majority of the emissions come from. And one of the main four ingredients of cement is aluminum oxide. So what Hydrova does is we actually recover aluminum oxide from aluminum waste. That's the rest of this material that's not aluminum metal is mainly aluminum oxide, basically the oxidized metal that has reacted with oxygen and hardened on the top of the furnace. We can take that and use it as one of the main ingredients to make cement that provides a low-cost, sustainable, locally sourced alternative to importing bauxite, which is where aluminum oxide would otherwise be coming from for these applications. We've actually formed a partnership with a company called CTS Cement that makes a product called Rapid Set Cement, which people might be familiar with, having seen it on the shelves of every Home Depot in the United States.
Like Quickcrete or something like that.
Yeah, essentially. So the rapid setting cements use a lot more aluminum oxide than regular cement. Basically, the amount of aluminum oxide is what determines the setting time. More aluminum oxide makes it set faster, less aluminum oxide makes it set slower. So these products like Quickcrete, Rapid Set Cement, they use a lot more aluminum oxide than ordinary Portland cements, and they are a great sort of off-taker for these aluminum dross recycling technologies.
Yeah, one of the things I also appreciated digging into concrete a bit more was, when you travel around, you look at the buildings and they're all different. And I've always thought about like, wait, where's the... And it's really because my understanding is cement is like the core part. But then what happens is as cement's shipped all around, people are now mixing it with whatever that local substance is, right? That kind of then makes the concrete, which gives it different colors depending on where you're at based on what's in the earth. Is that correct?
Exactly, yeah. So the aggregate, which is the rocks that you're digging up from various parts of the earth, can vary depending on where you're located. Can also vary on what kind of finished product that you want. If you see a concrete that looks smooth, like it has no rocks in it, it actually just has finely ground aggregates that are ground into a dust or sand-like consistency to get that texture.
One of the other things that your company also can do is create kind of a hydrogen byproduct that can be used in many different ways. You want to talk about that a little bit?
Yeah, definitely. Most people know hydrogen from the classic story of the Hindenburg, which was an old blimp that was filled with hydrogen and exploded, of course. That sort of gave everyone, a fear of the dangerous potential of hydrogen, but it also has incredible potential to provide a source of energy and be a carrier of energy because it's so volatile. Now hydrogen is being looked at to help decarbonize heavy industries like cement, like steel, being looked at for heavy duty transport, for aerospace, a company called Universal Hydrogen making planes that fly powered just on hydrogen.
One thing on that company in particular that's interesting is that the founder of that company was the CTO of Airbus. And I think his aha moment was looking at some of our ambitions for kind of a cleaner future, looking at aerospace in general and some of these targets. And I think his thinking was, there's no way we're going to get there. We're not going to mass produce enough jets to actually get there. So how can we retrofit jets with a hydrogen alternative. And I think he then, I don't know, a number of months now, I think he just did their first voyage up here in Moses Lake, Washington. It was cool to see, like a hydrogen powered plane. Like the only byproduct of that plane was water, and it was much quieter. I think it's a really fascinating thing. But I also think some of the challenges are just moving hydrogen around, like back to the Hindenburg comment, so that's another thing. And I know there's another company I've seen some people tapping into our, natural gas grid. I think the U.S. has the largest natural gas resource and the reserves on the planet, and it's very abundant. And so it's everywhere. So there's companies trying to figure out how can we tap into that, and then, closer to the source, can we convert it to hydrogen and then put it on planes and things like that?
Yeah, no, exactly. There's tons of new technologies, new applications for hydrogen that we've developed that are really, really exciting. But the key challenge is getting hydrogen to those applications to be able to fuel them. Where do we source the molecule from itself? How do you transport it? How do you store it? All of those really difficult questions. So right now, our hydrogen mainly comes from fossil fuels. It comes from natural gas in a process called steam methane reforming, or SMR. That basically takes natural gas, CH4, turns it into hydrogen, H2, but the C, the carbon, ends up becoming CO2 and going into the atmosphere, creating emissions. So one way to make hydrogen to prevent that is just taking the natural gas, doing SMR, and doing carbon capture. We call that
what's that? What's SMR?
Steam methane reforming. So that's taking natural gas and just making hydrogen and releasing the carbon into the atmosphere. And that's traditionally today how we make the majority of 90 megatons of hydrogen that the world makes per year. And that hydrogen is called gray hydrogen, on the sort of hydrogen rainbow, they call it. There's all sorts of colors that identify how the hydrogen was produced. So gray hydrogen is SMR with CO2 emissions. Blue hydrogen is what they call doing SMR with carbon capture. So that's basically doing steam methane reforming of natural gas and then just doing direct air capture, point source of that carbon before it goes to the atmosphere. Another interesting method is doing methane pyrolysis, which is more of an experimental technology right now, but it's basically cracking natural gas into hydrogen at really high temperatures and creating a solid carbon byproduct that can just be sequestered as a solid. And then, of course, there's electrolysis, which is green hydrogen, and using renewable energy and an electrolyzer to split water and produce hydrogen. To meet the future demands of hydrogen, which IEA projects to double by 2030 to 180 megatons, we're going to need to scale up all of these renewable sources, because the IEA also projects the amount of hydrogen coming from fossil fuels from steam methane reforming to decrease. So if the amount that we're making from steam methane reforming or gray hydrogen decreases, but the overall demand doubles, the amount that's coming from green or blue or other colors needs to drastically skyrocket. So we're going to need lots of electrolysis, lots of blue hydrogen, if we can do methane pyrolysis, as well as biomass gasification, landfill gas capture, all sorts of sources of hydrogen, and all of them are going to need to get scaled up. So Hydrova's approach is take the aluminum production waste and use that to do the aluminum water reaction and make hydrogen from any aluminum that can't be landfilled. So similar to other waste to energy processes, we basically take this waste byproduct that comes out of the aluminum recycling process, encourage it to split water and make hydrogen using aluminum metal rather than electricity. And then that solid aluminum oxide byproduct actually gets lumped in with our cement afterwards. So we not only make hydrogen from this waste, we also completely recycle it and repurpose it into valuable raw ingredients for cement production instead of sending it to landfill. So those are the two.
You're partnering then with recycling centers. Is that kind of the idea, and how you get in there you're doing this on site?
Exactly. Yeah. So our business model is to partner with companies that are called secondary aluminum processors. These are companies that are buying the scrap from your local recycling center and then actually melting it down and making new aluminum. And they're the ones that have to deal with this huge dross waste challenge. So the two sort of prongs of this technology, the two areas that help them is, one, not having to pay to process this dross waste and have it landfilled eventually. And two is also to be able to recover a little bit of hydrogen in the process that can be used to help decarbonize heavy industries like aluminum and cement without needing to be transported and moved all around. It's on site, so It's just directly reused without needing to move very far.
Yeah, I do hope a lot of this focus on climate gets people to really, it's awesome to see how humanity has evolved in the last 100 years. It's just, if you go back, think where we were 100 years ago and think it's just incredible.